Dear students, in today's session, we'll discuss all the important points related to important chapter called ray optics. So I'm going to start with the concept plane mirror. Now, when an object is placed in front of a plane mirror, the nature of the image that we get is always virtual because it's formed behind the mirror. It is erect in nature, and then most important, it has a unit magnification. Now, what do you mean by unit magnification? The object distance and image distance are equal, so that the magnification, the value of the magnification becomes 1. That's why it is called unit magnification. So if this is a plane mirror, and if a ray is incident on the plane mirror, this is the normal. The rays get reflected, so that this angle is angle of incidence. This angle is also angle of incidence. This is the direction of the incident ray. This is the angle through which the ray bends, and that's called angle of deviation. And that's equal to 180 minus 2i. If the object starts moving with a speed v in front of a plane mirror, then its image moves with a velocity of 2v with respect to object. If the object moves with a velocity v towards the plane mirror, then its image moves with a speed 2v with respect to. That's we can make use of the relative velocity in finding the value. So the value of the speed is equal to 2v. If I take two mirrors, two plane mirrors, which are placed in such a way that if theta is the angle between them, and then if a ray is incident on one of the mirror, after the reflection, it emerges from the second mirror. Now, in this case, the net deviation d is equal to 360 minus 2 theta. And here deviation d is independent of the angle of incidence. It is independent of I, which is angle of incidence. So I'm going to place one more mirror here. This is the plane mirror, and there is one more mirror which is again inclined by an angle theta. If a ray is incident on the first mirror at an angle I, and after reflection, it falls on the second mirror, and after the reflection at the second mirror, so this is the first, this is the second mirror. If the ray is get reflected in such a way that if it is parallel to the first mirror, if it is parallel to the first mirror, then the angle of incidence is equal to 2 theta minus 90 degree. So these are all special cases related to the plane mirror which you need to remember. So what is the equation? If I is the angle of incidence at the first mirror, and after two reflection, that is at the first mirror and if the second mirror, if the reflected ray is a parallel to the first mirror, then that angle of incidence is given by 2 theta minus 90 degree. If two mirrors are placed at an angle theta, and if an object is placed between them, then the number of images formed, n, can be found first by finding the ratio of 360 by theta, 360 degree by theta. So first find the value of n. Then if M is even, then the number of images is M minus 1. And if M is odd, then the number of images is M minus 1 for symmetric position of the object, for symmetric position of the object. If it is unsymmetric, symmetric means that the object is exactly, there is a midway between the two mirrors. If it is unsymmetric, that means if the object is closer to one of the mirror, then the number of images is equal to M. If M is a fraction like 7.2, then the number of images is the integer part of the number. If M is a fraction, something like this, then N will be the integer part only. And if mirrors are parallel, then M, here theta becomes 0, then the number of, the value of M becomes infinity, so the number of images also becomes infinity if the mirrors are parallel to each other. So these are the important points related to the plane mirror. So now let's learn all about the spherical mirrors. Spherical mirrors mainly are of two types, one concave mirror and the other is a convex mirror. So first we will discuss formation of images in the case of concave mirror, Formation of image in the case of concave mirror. A concave mirror is one in which the outer surface is silvered and the inner surface is reflective. So this is the pole of the mirror. This is the principal axis of it. And at a certain distance we have the principal focus. And again, almost at equidistance from F, there is a C, and that C stands for center of curvature of the mirror. Now, depending on where we place the object, we get different nature of the image. So here I'm going to write the position of the object. Then we have the position or the location of the image, and then the nature of the image. The first position that I'm going to consider is far away from the mirror, which is at infinity. When the object is placed at infinity, we get the image. Infinity means it's a parallel beam, like this. The rays get converged at F, so therefore the position of the image is at F. And the rays, you can see, they really converge at F, so therefore we get a real image. And all real images are inverted, and then we get a point image, which is called highly diminished image. That is when it is far away. Then we placed beyond the C, like this, beyond or far away from C. Then we get the image between F and C, between F and the C. The nature of the image is real, inverted, and then diminished. And when we place at C, the image is also formed at the same point, at C only. Real, inverted, and then the image is of the same size. And now when it is placed between F and C, between F and C, the image will be formed beyond the C, beyond the C. The nature of the image is real, inverted, and it's an enlarged image. Okay, enlarged. It's also called as magnified image. Now you can see here, when the position of the object is beyond the C, we get between F and C. And when the object is between F and C, we get beyond the C. So this is the good example for principle of reversibility of a rays, which tells that if the ray is incident in one direction, and when reversed, it will follow the same path in which the ray has entered. For example, if I take reflection, if this is the incident ray, then this is the reflected ray. And now if I consider this as the incident ray, the reflected ray will definitely come in that same path. So that's called principle of reversibility of the rays. And that's between F and C. Now when it is placed at F, so you can see when the object is at infinity, we get the image at F, and now the object is at F. So where do we expect its image to be? Definitely at infinity, at infinity. So what kind of image? So it's a real, and then inverted, and then it's a highly enlarged image we get. And when placed between F and P, it's between F and P. So only for this position, we get an image behind the mirror. And whenever we get image behind the mirror, it's not real because real images are formed in front of the mirror. So we get virtual image and erect. Real images are inverted, virtual image is always erect, and then it is a magnified or enlarged image. So you should remember these points or the table to solve again many questions related to the formation of the image by a concave mirror. In the case of convex mirror, we get only one nature of the image, only one type of the image, that is virtual, erect, and diminished. So we don't have different cases. So a convex mirror produces always a virtual enlarged diminished image, whereas a concave mirror, it produces either real image or virtual image. Virtual image produced by the concave mirror it's enlarged, whereas the virtual image produced by convex mirror is diminished. The distance between the principal focus and pole of a mirror is called the focal length. So on what factor the focal length of a spherical mirror depends? It depends only on one factor, which is the radius of curvature, that is F is equal to R by 2. So what is the relation between the focal length, object distance, and image distance? That relation is called mirror formula, and that's 1 by F is equal to 1 by U plus 1 by V. We can even write that, or F is equal to UV by U plus V. So we have few graphs here. The graph of U versus V is a rectangular hyperbola. The graph of 1 by U versus 1 by V is a linear graph. And in the case of plane mirror, U versus V is a straight line, and the value of the slope here is 45 degree. That means the slope is equal to 1. M is equal to 1. So this is the different graphs for spherical mirror, these two for spherical mirror, and that's for the plane mirror. linear magnification, M, which is the ratio of height of the object, height of the image to that of the height of the object. It's also equal to negative of the ratio of the image distance to that of the object distance. It's also equal to F minus V by F, and that's also equal to F by F minus C. So what is the significance of this linear magnification? If M is greater than 1, it means the image is enlarged. M equal to 1, the image is of the same size. If M lesser than 1 means it's diminished. If M is positive, then it's virtual and erect. And if M is negative, it's real and inverted. So this is the significance of the signs, and this is the significance of the value. So very important term to measure the size of the image when compared to the size of the object, and that's called linear magnification, and this linear magnification has no unit. So now let's discuss more on one of the optical phenomenon, which is a refraction. Phenomenon of bending of light when the ray travels from one medium to another medium is called refraction of light. And this refraction of light always obeys two laws of refraction, and the second law is called the Snell's law. And based on Snell's law, we can write 1n2, that is relative refractive index of second medium with respect to the first is equal to absolute refractive index of the second medium to that of the first medium. That is also equal to the ratio of velocity of the first medium to that of the second medium, and that's equal to a ratio of wavelength of the light in the first medium to that of the second medium, because velocity is directly proportional wavelength, and that is also equal to ratio of sin I by sin R, where I is the angle of incidence and R is the angle of refraction. So that's the relation between the various physical quantities. We can even write that's also equal to 1 by, it's a 2n1. That is relative refractive index of second medium with respect to the first is equal to the reciprocal of relative refractive index of the first medium with respect to the second medium. And relative refractive index is either it's a greater than 1 or it can be lesser than 1. That's a relative refractive index. Then we have absolute refractive index, which means the refractive index of a medium with respect to air or vacuum is called absolute refractive index, which is given by C by V. That's equal to lambda A by lambda M. That is also equal to sin I by sin R. And absolute refractive index is always greater than or equal to 1. It can never be less than 1. So equal to 1 for air or vacuum and greater than 1 for the other medium. Average value for glass 1.5, for water 1.33, for diamond 2.4. So like this, the value of n is different for the different medium, and refractive index has no unit. So it's a non-dimensional variable. It's not a constant, it's a variable. What's a variable? Because it varies from medium to medium. So I'm going to consider a parallel-sided glass slab having thickness T, and when a ray is incident, after the refraction, it emerges from the other surface in such a way that the incident ray and emergent ray are parallel to each other, so that the emergent ray shifts sideways laterally through a distance, and this perpendicular distance here between the incident ray and emergent ray is called the lateral shift, which is given by Ls is equal to T into sin I minus R by cos R, where T is the thickness of the optical medium, parallel-sided glass slab or parallel-sided optical medium. I is the angle of incidence, which is here, I, and R is the angle of refraction. So instead of reciprocal of cos R, you can even write T into sine I minus R into secant R. This is the other format of the same equation. Now this lateral shift is a minimum for normal incidence. Normal incidence. So what do you mean by normal incidence? Normal incidence is one where the angle of incidence is 0. And the lateral shift is a maximum. Here lateral shift is 0, which is minimum, and the lateral shift is maximum, whose value is equal to T. T is the thickness of the parallel-sided slab for grazing incidence. For grazing incidence. Now, what is grazing incidence? If the angle of incidence is equal to 90 degree. If the incident ray grazes the surface, then it's called grazing incidence, and mathematically we take that value of I to be equal to 90 degree. So this is about the lateral shift where the incident ray gets shifted laterally through a certain distance, and that perpendicular distance is called as the lateral shift. So here again I am going to consider two optical medium. This is the normal, this is the denser medium, and this is the rarer medium. A denser medium is one in which the absolute refractive index is more compared to that of the other medium, and the other medium is called as the rarer, whose absolute refractive index is lesser compared to the second medium. So now I'm going to consider the same situation here. So this is also the denser and this is the rarer medium. So I'm going to take an object here in this medium. So here, what is the object? And this is the interface. So from here I'm going to measure this depth, and that is called the real depth. dr is the real depth and O is the object here. And the observer is in the rarer medium. So object is in the denser medium, the observer is in the rarer medium. And when the observer sees, this object, due to normal refraction, it appears to be raised by certain distance. So it appears here, and that will be the image. So I stands for virtual image. And this phenomenon where an object in a denser medium, when viewed from the rarer medium, appears to be raised by certain distance. And that shift is called normal shift, and the phenomenon is called normal refraction. So therefore, here this is normal shift ns. And now from the interface to the position of the image, this is called the apparent depth, dA. So we find the real depth is greater than the apparent depth. And it's related to the refractive index n. So n is equal to the real depth by the apparent depth. We can even relate the normal shift ns. ns is equal to t, where t is the real depth, which is the dr, into 1 minus 1 by n. It is the real depth actually, that is dr, that's equal to t, and n is the absolute refractive index of the medium. So when the observer is in the rarer medium and when the object is in the denser medium, the object appears to be raised. Here, if the object is in the rarer medium, when viewed from the denser medium, so this is the object now, then it appears farther. So that's here, I. So from the interface to the object is the real depth, which is a dr. From the interface to the image is the apparent depth, And here the apparent depth is more than the real depth. So therefore, the absolute refractive index N is given by dA by dR. So see the difference here. And based on that, we get a formula for normal shift, which is Ns is equal to T into N minus 1. Instead of T, you can even write dr, where T is nothing but the real depth. So when an object placed in rarer medium, when viewed from the denser medium, it appears far. And this is the basis on which one can explain the change, apparent change in the height of a person standing inside a pool. So therefore, the height of the person standing inside a pool appears, or the person appears shorter because of the normal shift. Similarly, for an observer inside the pool, when viewed, the height of a person standing outside the pool, the person appears taller. That's because of the normal refraction. So whenever refraction takes place, so you need to remember certain basics of the refraction. If the ray travels from rarer to denser, if this is the incident ray having angle of incidence I, then the ray always bends towards the normal. So that R is the angle of refraction. So when the ray travels from rarer to denser, the ray bends towards the normal, so that I is always greater than R. When I is greater than R, the angle through which the ray bends is called as angle of deviation, which is D is equal to I minus R. Similarly, when the ray travels from denser to rarer, and if this is the incident ray, if this is the direction of the incident ray, the ray always bends away from the normal, And this is I, angle of incidence here. This is angle of refraction. So that angle of refraction is greater than the angle of incidence. Here angle of incidence is greater than angle of refraction. The angle of refraction is greater than the angle of incidence. So that the angle of deviation, the angle through which the ray bends due to the refraction, is given by R minus I. So these are the two important points, basics of the refraction, but they are very important to understand this entire chapter. So whenever ray travels from denser to rarer, the ray, this is the direction of incident ray, the ray always bends away from the normal. Then for particular angle of incidence, the ray grazes the surface. So this is the first ray, and this is the first refracted ray. This is the second incident ray, this is the second refracted ray. And for the third, the ray comes back. So here we have three situations where initially when the ray is incident at a particular angle, the ray undergoes refraction. And then for a particular angle of incidence, the ray grazes the surface, and that particular angle is called as the critical angle for the pair of media. So at the critical angle, the angle of refraction is equal to the 90 degree. At critical angle, the ray grazes the surface, so the angle of refraction is equal to 90 degree. And for any angle above the critical angle, the ray undergoes total internal reflection. And if the angle of incidence is lesser than the critical angle, it undergoes only a refraction. So when it undergoes refraction, we can calculate the angle of deviation is equal to R minus I, because R is greater than I. Why R is greater than I? Because the ray travels from denser to rarer. When R is 90 degree, so angle of deviation is given by 90 degree minus I, because R is 90 degree minus. And then when the ray undergoes a total internal reflection, we have to make use of the angle of deviation that we have used in reflection, which is 180 minus 2I. So this is how we can find the deviation in a phenomenon called a total internal reflection, for which two conditions are very much essential. One, the ray must travel from the denser to the rarer medium, and the angle of incidence must be greater than the critical angle for the pair of media. So without satisfying these two conditions, there cannot be any total internal reflection. The critical angle is related to the refractive index, that is sin C is equal to N2 by N1. So when we write N2 by N1, this numerator is the refractive index of the rarer medium divided by refractive index of the denser medium. It cannot be other way around, because if you write refractive index of denser to the rarer, refractive index of the denser is greater than that of the rarer. So the ratio comes greater than 1. And the value of the sine function cannot be greater than 1. So therefore, it has to be refractive index of the rarer to the refractive index of the denser medium. That's how we can calculate the critical angle. This we can even equate like this. That is also equal to N2 by N1 can be written as a V1 by V2, because the speed of light and the refractive index, they are inversely related. That is also equal to lambda 1 by lambda 2, because the velocity and the wavelength are directly related. So this is how, by knowing the refractive indices, we can find the critical angle. But if one of the medium is air or vacuum, then the refractive index, N, absolute refractive index, is given by N is equal to 1 by sin C. That is also equal to C by V. That is also equal to lambda A by lambda M. So you get to see two C's here. One capital C, the other is the small letter c. Capital C is the critical angle. Small letter c is the speed of light in vacuum. So related to critical angle, so we have a special case where inside a pool of water, which is at the depth h, if a source is placed, source of light is placed, it emits light in all directions. Then once it reaches a particular angle, it undergoes total internal reflection like this. First it grazes, beyond that it undergoes total internal reflection. So that only this portion of the pool is get illuminated, having circular shape. That illuminated part of the pool, surface of the pool, has circular in shape. But this entire structure is a conical structure. So this is critical angle. Even this is also critical angle. R is the radius of the cone. H is the height, or sorry, not the height, the depth of the source or depth of the pool. And R is the radius of the illuminated part, which is circular on the surface, but from the bottom it's conical. Now this R and H are related by R is equal to H tan C, which can also be written as H by root of n square minus 1. And based on that, we can even write n is equal to root of r square plus h square by r. So they are all the same equation, different formats of the same equation. So special case, all the formulas you need to remember, and it's applicable only for the situation which is given here. So one more set of equations which is important is refraction through a prism. So when refraction takes place through a prism, one of the face which is highly polished is called as the base, and these are the two refracting faces, and A is the angle of the prism. A monochromatic ray is incident on one of the face, it undergoes a refraction, and then further it emerges out of it. So refraction takes place twice, once at one of the surface and again at the other surface. At the first surface, I1, R1 are the angle of incidence and angle of refraction. Here R2, I2, we interchange the variable. R2 is the angle of incidence and I2 is the angle of refraction. So deviation at the first phase is given by I1 minus R1. Deviation at the second phase, D2 is equal to I2 minus R2. The net deviation is I1 plus I2 minus A, whereas the angle of the prism given by R1 plus R2. The refractive index, if it is absolute, is given by sine I1 by sine R1 is equal to sine I2 by sine R2. That is if it is absolute. Suppose if the prism is immersed in a medium, surrounding medium, then n by ns, where ns is the refractive index of the surrounding medium, which is given by sine I1 by sine R1 is equal to sine I2 by sine R2. Sine R. Here I1 and I2, so need not be equal. If they are equal, if I1 is equal to I2 is equal to I, or R1 is equal to R2 is equal to R, then we say that this prism is in the minimum deviation position. So D minimum, it is denoted by capital D and it's called as the angle of minimum deviation. And when the angle of deviation is minimum, the refracted ray inside the prism, the refracted ray inside the prism is parallel to its base. No, it's parallel to its base. And when they are equal, we can find the value of this I to be equal to A plus D by 2 and this R to be equal to A by 2. And based on that, we get a new formula for n, which is n is equal to sine A plus D by 2 divided by sine A by 2, which is also called as a prism formula. If the prism is immersed in a medium having refractive index ns, then n by ns is equal to sine A plus D by 2 plus D by 2 by sine A by 2. So when a prism is immersed in water, its a deviation nearly decreases 4 times actually. It decreases 4 times. So that means the new angle of deviation will be equal to initial angle of deviation by 4. Okay. Decreases means we have to always divide by that particular factor. Increases means we have to multiply by that factor. So this is regarding the prism. Now if the angle of the prism is very small, of the order of about 10 degrees, then we call it as a thin prism. So angle of deviation of the thin prism is given by D is equal to A into n minus 1. And the equation clearly indicates that the deviation is independent of the angle of incidence. If it is surrounded by a medium, then D is equal to A into n by ns minus 1. And here also we can write like this: deviation in water, it always decreases 4 times, is equal to deviation in air by 4. So deviation in water to that of the deviation in air is divided by 4, or the ratio is 1:4. That means in water it always decreases by a factor 4, decreases by a factor 4. And there are 2 special cases, that is for equilateral prism when A is 60 degree and when the refractive index is root 2, then the angle of deviation is 30 degree, and if the refractive index is root 3, then the angle of deviation is 60 degrees. So these are the 2 special cases. For an equilateral prism having refractive index root 2, the angle of deviation is 30. And for an equilateral prism having refractive index root 3, the angle of deviation is 60 degree. So next we have an optical device called lens. A lens is an optical device bounded by 2 surfaces, out of which at least one must be spherical. And the focal length of such a lens is given by lens maker's formula, which is 1 by f is equal to n2 by n1 minus 1 into 1 by r1 minus 1 by r2, where r1 and r2 are the radii of curvature of the two surfaces. n2 is that of the material of the lens, this is of the lens, whereas n1 is that of the medium, surrounding the medium. Suppose if it is in air, then we write 1 by f is equal to n minus 1 into 1 by r1 minus 1 by r2. If I rearrange this, and then I'll get an equation for refractive index that is to be equal to 1 plus r1, r2, r1, r2 here into f, r1, r2 divided by f into r2 minus r1. Same equation rearranged in this particular manner. Now, when lens is immersed in water, its power and the focal length are related like this: f is equal to 1 by p. So, when the power increases, focal length decreases, and when the power decreases, focal length increases. So, when a lens is immersed in water, its focal length increases 4 times. So, focal length of the lens in water is 4 times the focal length of the lens in air, whereas the power, it decreases. Power of the lens in water is 4 times lesser. That means the power of the lens in air by 4. So, focal length increases whereas the power decreases, and these equations are valid only when the lens is immersed in water, not in any other liquid. Okay, it's applicable only for water. Now, if the radii of curvatures are same, then we call it as equiconvex lens, for which the focal length is r by 2 into n minus 1. If it is concave, this is for convex. If it is concave, then we write the equation as f is equal to minus r by 2 into n minus 1, because focal length of a concave lens, focal length and its power is always a negative. For plano-convex lens, plano-convex. A plano-convex lens is one where one of the surface is plane, the other is a convex. Then the focal length is given by r by n minus 1. So here it is r by 2 into n minus 1, there it is r by n minus 1. That's for convex. If it is concave, f is equal to minus r by n minus 1. When we place an object in front of a convex lens, it produces image, and that distance between the object, image and the focal length is given by a formula called lens formula, which is 1 by f is equal to minus 1 by u plus 1 by v. And the linear magnification is given by hi by ho and minus v by u. What I am writing right now is that of the mirror, minus v by u. That's equal to f minus v by f and then f by f minus u. This is the equation related to the mirror. Okay, so let me write it. This is the mirror. Now, to write the equation for lenses, what you need to do is, wherever there is u, apply the minus sign for it. So this is mirror formula. Wherever there is a term u, if you apply the minus, then it becomes a lens formula. hi by ho, apply minus. Already there is a minus, so it becomes a plus. Then f minus v by f. F by f, there is a u, again apply minus sign, so it becomes a plus. So by changing the mirror formula or equation for magnification, we can get the formula related to the lens. So what are the changes to be made? Wherever there is a u, replace it as a minus u. Then now the same equations which we have used for mirror is now applicable for the lenses. And the nature remains the same, that is m greater than 1, m lesser than 1, m equal to 1, m positive and M negative. M greater than 1, enlarged image, M lesser than 1, diminished image, M equal to 1, image of the same size, M positive. It's virtual and erect, M positive. M negative means it's a real and inverted. So this is how we can make use of these formulas. So very important. There are again a lot of numericals based on these equations. The property of concave mirror is similar to that of convex lens, or we can say that the property of the convex lens is similar to that of the concave mirror. A concave mirror is one which produces either real or virtual images. Similarly, convex lens also produces either real or virtual images. And that's what we are going to discuss now. That is formation of images by convex lens. In the case of convex lens, the point where the rays get focused is called the principal focus, and there are two such focus or foci are there. And then almost again equidistance, we have double the focal length, which is denoted by 2f, and the point inside the lens is called the optic center. Now, the position of the object, and then we have position of the image, and then the nature of the image. When the object is placed at infinity, the image will be formed at f, and it's real inverted, and it's a highly diminished image. That's when it is placed at f. And when placed beyond 2f, the image will be formed between f and 2f. Image will be between f and 2f. And the nature of the image is real, inverted, and diminished. When the object is placed at 2f, here at 2f, the image also will be formed at 2f. The nature of the image is real and inverted, and then same size. The image is of the same size. And when it is placed between f and 2f, between f and 2f, so again you can use the principle of reversibility. When it is between f and 2f, you will get the image beyond 2f. The nature of the image is real and inverted, and then it is a magnified image or enlarged image. And then when it is placed at f, the image will be at infinity, and it will be real, inverted, and then it's highly enlarged or highly magnified is the other word used. Highly magnified. And when it is placed between O and F, it's between O and F, the image will be formed on the other side, it will be formed on the same side, okay, not on the other side of it, it will be formed on the same side. See, the difference between the real images in concave mirror and the real images formed in convex lenses is that in the case of mirror, the real images are formed in front of the mirror. Real images are formed in front of the mirror or on the same side as that of the object. Whereas in lenses, object will be on one side of the lens, real images will be on the other side of the lens. So that's the difference. So that's why when the object is placed between O and F, the image will be formed on the same side as that of the object. Okay, so between O and F, it's on the same side. And what's the nature of the image? It's virtual and then erect and then it is enlarged. So you can see this formation of the image is almost similar to that of the concave mirror. Only difference is, instead of C in mirror, we use the point 2f, because we don't have a center of curvature as such here. So for every surface there is a center of curvature, but for the lens as such we don't locate the position of the center of curvature. So that's why we write it's a 2f, which is twice the focal length. Okay. So cable again similar to that of the concave mirror. A convex mirror has the same property as that of the concave lens. That is, the nature of the image formed by concave lens is virtual, then erect, and then diminished, similar to that of the convex mirror. So here we have a convex lens of focal length f. F is the focal length of the lens. And now this lens is cut into two parts like this. It's cut into two parts, so that this is part 1 and this is the other part of it. And now these two parts are placed in contact once again, something like this. So f is the focal length. First it's cut perpendicular to the principal axis. So now what is the focal length of each part, and when they are placed in contact once again, what is the focal length and the power of the combination? So here let f and p with the focal length and power of the given convex lens. It's an equiconvex lens and it's cut exactly into two halves. So it's very easy to analyze by taking this factor, which is power. Power of a lens depends on the radius of curvature of the two surfaces. The entire power depends on the radius of curvature. Moment you cut that into two halves, it loses one of the curvature. That means its power will decrease by that factor. So when it loses one of the curved surface, its power becomes p by 2. So the power of this part is p by 2, the power of this part is p by 2, because it has lost one of the curved surface. And we know that the focal and the power are inversely related. So when the power is halved, the focal length doubles. So it's a 2f and 2f. So power of the two lenses is p by 2, and their focal length is 2f and 2f. And now when the lenses are placed in contact like this, so power of this is a p by 2, power of this is also p by 2. The power is get added up so that the effective power is a p and effective focal length is f. Here also, when these two are placed in contact, the power is get added up, p by 2 plus p by 2. So effective power becomes a p and the focal length becomes f. So this is one of the situation where when a lens is cut in a plane perpendicular to the principal axis of the lens. So we have one more similar situation where a lens is cut. The lens is cut. Along the plane of the principal axis. It's cut like this. Along the plane. So this is the principal axis. Earlier it was cut perpendicular to the plane. Now it's cut the plane passing through the principal axis. And then we get two halves like this. This is one half and this is the other half of it. Then they are arranged like this. This is one of the case, situation number 1, and this is the next case. So when the lens is cut, okay, let's P and F be the power and the focal length of the original lens. And now when the lens is cut in this plane, if you check these two parts, both the parts have that radius of, or the curvature is still intact. There's no loss of the curvature is still the same. It has lost part of the area but not the curvature. So that is the reason why the power of both the parts remains the same. There is no change in the focal length and the power. So now these two parts are placed in contact. So this is P and this is P. The same two parts are placed in contact. So what is the effective power? Effective power here is P plus P, which is 2P. So when the power is doubled, what happens to the focal length? Focal length is half. So therefore the new focal length is half of the initial focal length. Now to analyze this particular diagram, you need to understand that in the case of convex lens, the axis passes through the thinner portion of the lens. The axis passes through the thin portion. So here, this particular lens has a power P. This also has a power P. But you can see the axis is here. And that axis passes through the thin portion. Can you see that? This is the thinner portion, this is the thicker portion. So thin portion of the lens, thin portion. That's why that particular part, even though it's a part of the convex lens, but it behaves like concave because the axis passes through the thinner portion of the lens. So that's why the power of that is taken as a negative. So positive for the first lens, negative for the other, effective power is a 0. So therefore for that combination, the effective power is a 0. So if the power is 0, what is the focal length? Reciprocal of 0. Reciprocal of the 0, which is infinity. So the focal length is infinity. So this is again two special cases where a lens is cut in two different planes, and then when they are joined, what is the new focal length, what is the new power? So that can be understood using this diagram. And all this analysis, we can do it because of the concept of combination of the lenses. Combination of lenses. Where when number of lenses are placed in contact, the effective focal length, the reciprocal of the effective focal length is equal to sum of the reciprocal of the individual lenses. Whereas the power of the effective lens is equal to sum of the power of the individual lenses. And the main advantage of the combination is the net magnification is equal to the product of the magnification produced by the individual lenses. This is the main advantage. The magnification is get multiplied, they don't get added up. Multiplication gives a larger number than the addition. And if two lenses are separated by certain distance d apart, when we write this equation, we assume the lenses are in contact. Suppose if the lenses are distance d apart, then the reciprocal of the focal length 1 by f is equal to 1 by f1 plus 1 by f2 minus d by f1 into f2. Suppose if there is some medium in between having refractive index n, then we can write 1 by f is equal to 1 by f1 plus 1 by f2 minus d by n, where n is the refractive index of the medium between the two lenses, divided by f1 into f2. We can write the same equation in terms of the power. P is equal to P1 plus P2 minus D P1 P2. And this equation we can write like this, P is equal to P1 plus P2 minus D P1 P2 by N. So this is without medium between the lenses, and this is with medium having refractive index N. So I am going to consider a plano convex lens having focal length f given by r by n minus 1. This is the focal length. And now the plane surface of the lens is a silvered. Plane surface is silver. So the focal length changes when it's silver, because now it acts like combination of a plane mirror and a lens. So the new focal length is given by f dash is equal to f by 2. And this particular combination, now it behaves like concave mirror. Concave mirror. In the same lens, if curved surface is silvered, then the new focal length f dash is equal to r by 2n, and this also it behaves like concave mirror. So these equations are valid even for plano-concave lens. Plano-concave lens. So I'm going to consider now a equiconvex lens having focal length f is equal to r by 2 into n minus 1. And one of the surface is a silver, and now it acts like a combination of concave mirror and convex lens. Here also it acts like a combination of concave mirror and plano-convex lens. So in this case, the new focal length is f dash is equal to r by 2 into 2n minus 1. And this new focal length, it behaves like concave mirror. Concave mirror. So again, same equations are valid even for concave lens. Concave lens. So therefore, these are the three different cases which you need to remember. Plano-convex lens, plane surface is silvered. Plano-convex lens, curved surface is silvered. Equiconvex lens, one of the surface is silvered, and moment you silver, it acts like a combination of a mirror and a lens. So focal length changes, and these are the new value of the focal length after the surface are silvered. Okay. Next, we have three important optical instrument. One is simple microscope. Then we have compound microscope. Then we have telescope. If you compare the heights of the object and the image, then we can measure a magnification called linear magnification. By comparing the angle subtended by the object and the image at the eye, we can measure the angular magnification. It is also called as a magnifying power. So what is the magnifying power of a simple microscope when the image is formed at near point? At near point. It is also called as the normal adjustment. So m is equal to 1 plus d by f, where d is called the least distance of distinct vision, which is 25 centimeter for normal eye. In the case of compound microscope, that m is given by L by f naught into 1 plus d by fe. Because in compound microscope, there are two lenses. One is objective lens and the other is eyepiece. Fe is the focal length of the eyepiece and Fo is the focal length of the objective lens, and L is the length of the microscope, which is basically the distance between the two lenses, and capital D is same, which is 25 centimeter. And in telescope, the magnifying power is given by Fo by Fe, focal length of the objective lens to that of the focal length of the eyepiece. And the length of the telescope is given by the sum of the focal length, which is Fo plus Fe. So that will give you the length of the telescope. So these are all important equations of the important chapter called ray optics. So before solving any questions, it's important to revise all these formulas, and only then you'll be able to attempt more questions, and then you'll understand those questions better. Thank you.